Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. The usual reminder that if you do enjoy the show, please consider supporting us through Buy Me a Coffee. It really helps us to keep making the show. Today, I've got with me Matt Butrovich, who will be telling us everything we need to know about database proxies. Now, this specifically is some work that Matt published at VLDB last year, and it's a paper called Tigger, a database proxy that bounces with user bypass. Welcome to the show, Matt.
Yeah, thanks for having me.
The pleasure's all ours. Cool. So let's get started then. So can you tell us more about yourself, Matt, and how you became interested in databases and database management research?
Sure. So for context, I'm currently a PhD student at Carnegie Mellon University in Pittsburgh, Pennsylvania, hopefully in my last year. And my background is I've sort of worked my way up the computing stack in some ways. So my undergrad education and work experience was all in embedded devices mostly. So specifically storage devices, things like hard disk drives, SSDs. And so thinking about how does your data become durable at a physical device level. And then when I started my master's at CMU, sort of working my way up the stack, thinking about things like file systems, distributed file systems. And then I got to my advisor, Andy Pavlov's graduate course on database systems. And his enthusiasm was just infectious. And so I was really sort of interested in these systems that touch on so many aspects of computer science fundamentals, theory, programming languages, storage systems, network systems, and relating that to things that I had sort of seen before. So a database system's write-ahead log is just a file system's journal. And I had seen things like ACID properties and two-phase commit before. So I had a lot of context to sort of step into the database system world and start working with Andy. And a year later, I was his PhD student. And it's such a great problem space to work within the database system community because you have so much potential impact. Like every major application is backed by a database system. So there are so many opportunities for people to bring their sort of diverse backgrounds, different expertise to bear in this sort of huge problem space and have a real impact on applications that people interact with every day.
Yeah, for sure. It's there's plenty of problems to be getting stuck into for our careers, and we're probably always going to have a job as well, right? Because it's that important in most modern stacks these days. Cool. So we're going to be talking about proxies today, but maybe we could start off with some background, and you can tell a listener how modern applications actually connect to databases these days, and kind of what are the general problems with the approaches that they take today.
Right. So, I mean, there are a couple trends that stand out with the way sort of modern cloud applications, I guess, connect to database systems these days. And on the one extreme, you have this independent scaling at the application layer, this sort of elastic compute that software applications designed for the cloud use now when they need to throw more resources at the problem. You suddenly have dozens or hundreds more servers. And these are opening hundreds or thousands more connections to the backend database system. So you have this challenge of persistent connections and this huge connection scaling challenge that's created by this sort of elasticity at the application layer. And at the other end, you have serverless computing, which is creating the opposite problem or in some ways a contrasting problem to this sort of high connection count scale, persistent connection scaling issue of very short-lived ephemeral connections that go through all the trouble of connecting to the database system, authenticating, often going through an SSL handshake, only to submit a single query and then disappear. And these two extremes are challenging for a couple of reasons for database systems. At the persistent connection issue, when you get into large numbers of connections, the database system just sort of runs slower and slower. So we can see query latencies go from single milliseconds to hundreds of milliseconds because the database system has to apply concurrency control logic to more and more connections in order to successfully commit transactions. Even if the connections aren't even doing anything, each idle connection in something like Postgres takes on the order of megabytes of memory. And that's before each connection starts populating its caches. So if you have tens of thousands of connections, you're suddenly using gigabytes of memory to do nothing. And then at the other extreme with these short-lived serverless connections, again, I'll use Postgres as an example. Postgres uses the process model for parallelism. And so every connection that shows up, it has to fork a process. And this is a pretty heavyweight operation for the operating system to deal with. And every time a connection goes away, it has to reap that process. It has to, especially because Postgres relies on shared memory, there's just a lot that goes into forking a single process. And this repeated forking and reaping creates a lot of challenges for database systems to keep up with.
So the solution to this is a proxy. Can you tell us about what we actually mean by a proxy in this context and the benefits that they provide?
We're talking about proxies that understand the actual application protocol. In this case, a database system's network protocol, like wire protocol. Like so they speak, again, for example, like the Postgres wire protocol. They sit right in the middle between the front end clients and the back end database systems. Clients connect to them as if they're connecting to the database system. So they speak the same authentication protocol. The client's sort of oblivious that they're talking to a proxy at all. They issue their transactions, their queries, they get the results back as if they were just interacting with the database system. So the way proxies actually help sort of the problems we described before, because it seems a little counterintuitive that putting a box in the middle, like a middleware in between a client and a backend database system, would actually help your application run better. The big thing that they do is, at least when we're talking about like a high number of connections, is something called connection pooling. So you can stick 10,000 clients in front of a proxy. They all connect to the proxy, and the proxy can actually reduce the number of persistent connections to the backend database system, assuming sort of like these 10,000 clients aren't like maxing out their throughput and completely like saturating their connections as fast as possible. These proxies can actually multiplex the transactions from the front end to a smaller number of backend connections. So like you may be able to serve 10,000 front end clients over 40 backend connections by just sort of interleaving the operations on the persistent connections to the database system. So by having a fewer number of connections at the database system, you sort of get the benefits of serving 10,000 clients, but you don't actually have the database system reasoning about that many clients, and it's able to operate more efficiently because those data structures are smaller. So we've seen, on the order of like single digit milliseconds going up to tens to hundreds of milliseconds when you have tens of thousands of connections. You can bring that latency back down by putting a proxy in between, by actually doing connection pooling. At the other extreme, with sort of serverless setups, I mentioned things like the SSL handshake, the cost of forking a process. That's all painful on database systems. The proxy sort of absorbs all that cost, and you're sort of pushing the computational cost to a different application, oftentimes a different box, to absorb the CPU cycles that have to be spent on connection setup and connection teardown, authentication, and logging in, and all those other things. And the backend database system just gets to focus on running queries, which is really all we want it to do. So yeah, like I said, it seems a little counterintuitive to putting a box in the middle can actually make your system run faster. But like as sort of like a simple example, like I think in the paper we showed very early on running a workload with 10,000 clients and running like 2,000 transactions per second on a standard benchmark. I think it was YCSB. Mm-hmm. You could bring something like the P99 latency down. It cuts it in more than half, which is a huge number when people are reasoning about P99 latency. And you pay a minuscule increase in minimum latency because you're doing an extra network hop. But if you can pull in that P99, in general, what we saw is putting a proxy in between would compress the distribution of transaction latencies because the backend database system wasn't having to reason about as many connections, and its concurrency control protocols could run more efficiently. Nice. I guess the other thing I'll say about proxies is the application isn't limited to just connection pooling. People are doing a lot more interesting things with them with respect to like automatic sharding. So if you think of like traditional middleware stuff like Vitess, they're doing, that was a way to scale out MySQL. People use them for workload mirroring to sort of replicate a workload across production and staging environments. Other people use it just for security reasons, credential management, transparent upgrades of your database system in the background. You put a proxy in the front and you can suddenly just switch the traffic transparently between an older version and a newer version. I think one of the engineers at Meta talked to me at VLDB and said, yeah, they have more people working on their MySQL gateway, effectively their proxy, than they do actually have working on MySQL. It's such a core component of getting performance out of MySQL for them that they actually have way more engineering on their proxy.
Well, yeah, I mean, that reduction in P99 latency there is, I mean, that just makes for such a better user experience as well, right? That sort of reliable compression, that distribution is just makes the usability and the experience of the system a lot nicer straight away. So I can see why in this scenario, the indirection layer is a massive win. And that's so interesting that kind of they've got more people working on their gateway than their actual sort of, I guess, like deeper down the sort of database stack. A question on that though is how much of this and the need for these proxies is down to the fact that we are basically using database systems that are 30, 40 years old, like and kind of database systems that have been built today kind of having all these sorts of features within them already, or are they kind of also making the same design decisions that Postgres made, that MySQL made? Like how do they look compared to the old systems, the new systems?
Yeah, it's interesting to see how the need for proxies is changing when you talk about a newer system. I mean, everything I keep talking about is like in the context of Postgres, which, like you said, is an old design, and a lot of systems have inherited those decisions when we look at how many systems have forked Postgres. But in modern times, like it's actually getting interesting. Like, what is a proxy these days? Because a lot of these cloud native database systems, you look at like a modern Postgres replacement like Neon, who's trying to do serverless Postgres. They've got a proxy in the front, but they're using it to sort of figure out which serverless compute system they want to, like, the user submits a query. That's sort of the persistent connection that the client sees. You submit your you submit your query to it, and then they need to route that to an appropriate serverless, ephemeral compute node to run your query. I think we're increasingly seeing more things, which is sort of why probably Facebook or Meta calls it their gateway, right? Like this sort of persistent connection that the client connects to, or the application connects to, submits queries, and it sort of obfuscates what's happening on the back end of these database systems. How you choose to, what sort of back end you send that query to, how many compute nodes you spin up. I could argue something like how you interact with a modern cloud data warehouse like Snowflake. It's a web interface. You submit a query to it. You get your results back. Is that a proxy? I don't know. The lines start to get very blurred between what is this persistent front end that clients connect to, submit queries to, and then they get routed to some sort of obfuscated cloud backend. And I think we're going to see more and more of this sort of stuff. Actually, it seemed like there was an interesting resurgence. Poly stores are back in a big way. That was sort of like a big discussion and I feel like at VLDB this year, of just like, there's all these heterogeneous cloud database systems that companies are relying on to solve their problems. And people are like, well, how do we consolidate this into a front end that figures out, well, which backend would actually be the most efficient way to run this query? So if anything, I think we're going to call them proxies less and less. I think proxy implies like a very simple application that's not applying a lot of logic. And it's just sort of this front end that is sort of the persistent, to steal the phrase, gateway that users submit their queries to interact with the database system. And sort of what happens behind the scenes is sort of obscured from the user. So yeah, like to your point, like our proxies probably were brought into the industry to solve sort of scaling problems for systems like MySQL and Postgres. Mm-hmm. And they still solve that problem in a lot of ways. And it still lets a lot of people get off the ground with sort of less elaborate database system solutions. And then you can start with a proxy to start to scale things out. But we're going to see the capabilities continue to grow as people use them for things like automatic sharding and putting maybe query caches in there, stuff like that.
Yeah. Interesting. They become kind of more, I guess, general purpose, or having a lot of functionality kind of absorbed into them. What are a few of just to kind of drop some names in, some of the most common proxies at the moment out there that people use?
So on the Postgres side, PG Bouncer is the one that people always start with. It's been around for ages. There was PG Pool 2 as well. And PG Pool 2 made its name because, it was around before Postgres had native replication. So if you wanted to do, like, PG Pool 2 was sort of solving the problem of bringing sort of distributed durability to Postgres systems before Postgres sort of had a lot of those native capabilities. On the MySQL side, you've got things like Proxy SQL. I think I mentioned, like, again, Vitesse markets itself as more of a middleware, but again, it was a proxy to help them scale out MySQL. And then there's a number of folks that have sort of looked at PG Bouncer and started to either rewrite it or fork it or do different things with it. So the folks at Yandex actually wrote their own Postgres proxy they call Odyssey, which is meant to be like a much higher performance version of PG Bouncer because they found it a little too restrictive. And then the folks behind PostgreSML have a Rust-based proxy that they've been working on for a year or two called PGCat that they mostly use for sharding, but it also does connection pooling as well. So there's a number of these out there because ultimately, like the application logic is pretty simple. Depending on how many features you want to put in there, they're pretty simple applications.
Yeah, nice. Cool. So yeah, I guess some of these proxies that we have, some of the current sort of proxy implementations, you identified there's some pitfalls with them and they're not perfect, hence the paper. So what are the problems with the sort of the current family or the current iteration of these proxies?
Yeah, so I mean, I sort of alluded to it with the fact that people are, in particular, someone like Yandex, they were looking at something like PG Bouncer and saying like the performance just isn't there. We need to write a multi-threaded implementation. PG Bouncer is a single-threaded application. It's written in C. It's a very simple application that just kind of looks at the Postgres protocol and manages connection pooling. But like if you want to get better performance out of it, particularly parallel performance, you have to rely on things like running multiple instances of PG Bouncer on the same box, either put them on different ports with a sort of L3, L4 like HA proxy in front to sort of load balance across multiple PG Bouncers. You see people with that sort of setup. Other folks can use, I think the reuse port option in Linux now lets you run multiple applications off the same port and it'll do load balancing. So you can run multiple PG Bouncers on the same box, listening on the same port, and sort of Linux manages that port reuse for you. But in general, like PG Bouncer setups got very complicated as people wanted to get performance out of them. And there was one blog post, I want to say it was from Figma, where they were looking at where's PG Bouncer spending its CPU cycles when this thing's maxed out. And they actually found it was burning all of its CPU cycles effectively on system calls, mostly on mem copies when it's doing SSL read and SSL write. That's where it's burning all its CPU cycles. And that's sort of a new challenge for us as we look at building high performance applications, whether they're database systems, whether they're network applications, or something kind of in the middle like a database proxy, of what do you do when your application logic is so lightweight in something like PG Bouncer that sort of getting access to the data from the through the operating system, through the OS services, is sort of becomes your bottleneck. And how do you design applications in that sort of problem space?
Awesome, cool. So kind of when you're thinking about it, you kind of come up with this alternative architecture for solving this problem, which you call user bypass. So can you tell us more about user bypass and how it helps maybe solve some of this kind of the bottleneck that the operating system can be in this scenario?
Right. I mean, so for a little context on user bypass, I want to talk about kernel bypass for a second, right? So like I'm describing this problem of, okay, your application logic is very lightweight. You want access to your IO data and you're paying this huge cost to use the OS services. So, something that's been around for decades now at this point was this notion of, okay, do kernel bypass. So it's like for networking, if you have an Intel NIC, you can get Intel's DPDK framework and you can design an application around kernel bypass and the DPDK framework that lets you sort of read data directly from the network device, bypass the OS stack, get it to user space as fast as possible. It's sort of the idea behind kernel bypass. Mm-hmm. Get your data up to the user space application logic as quickly as possible and then send it back out. And you can do that. There are applications in production that use kernel bypass. In practice, it's been, we've looked at it. It's been tough to use in general because the API has generally not been stable. So putting something into production has its pitfalls of like your application release is going to be tied to a specific driver release. If a new driver comes out, you need a new application release and vice versa. Getting good performance out is really tough, depending on how you designed like the work queue and multi-threading in your application layer. If are you polling on a single core? Are you event driven? Things like that. So we sort of argued kernel bypass is maybe not the solution here, which is where we said, okay, well, instead of bringing your application data up to user space as quickly as possible, what if you could sort of push your application logic down to the data as closely as possible? And so we've said, okay, well, that's user bypass, effectively bypass user space. And this sort of it's not a new idea. This notion of kernel offload, extensible operating systems, SpinOS in the 90s, exokernel, people have been talking about like operating system extensibility and embedding more application logic in the operating system for a long time. If you look at the extreme end, you have unikernels. So where we argue we're reasoning about things a little bit differently is we're relying on these new extensibility features in the Linux operating system called eBPF. And people debate on whether it still even stands for the extended Berkeley packet filter. People just say it's eBPF now. That's the technology. It's not an acronym anymore. Whatever, let them argue about it. But the idea is we can use this extensibility feature in the Linux kernel that allows you to write these sort of safe event-driven programs that aren't quite as invasive as loading something like a kernel module, which has security concerns, or even compiling your own kernel. It sits in this nice middle ground that actually allows us to extend the operating system in a way we really couldn't before with these earlier efforts, either due to lack of a standard API, lack of adoption with things like, again, like SpinOS, Exokernel. Like they were academic efforts, but we never really saw anything in the real world that we could use to sort of achieve this idea of user bypass and designing applications that either sort of take a hybrid approach to some operations happening in user space, some operations happening in kernel space, or just entirely pushing all of our application logic into the kernel and never having to go to user space at all.
Yeah, nice. I just want to ask you a quick question about eBPF. And you said before some of the old sort of attempts at sort of in this space weren't very stable and the API wasn't stable. Is that a different story with eBPF, right? That is something that you can use it in production with a lot more sort of guaranteed, and that you aren't going to be tied to a particular version, like you said, or anything like that?
Yeah, I mean, I'll be honest. It's a little bit of a cop-out on my part. eBPF has absolutely been a moving target the last 10 years. I think eBPF was officially branded that in like 2013. So it's been a decade now. In the 6 years I've been a grad student, the ecosystem has changed wildly. Now it's getting better, like strictly for the better. Like the way I had to write eBPF programs 5 years ago is very different than how I write them now. And the tooling and everything has gotten better, but that doesn't mean it hasn't been a moving target and APIs weren't stable for a few of those years. I think we've reached a point where I could actually, endorse it in a production environment, and like for what little that carries as an academic graduate student saying you should use eBPF, but like I mean, it is in use now. Like,
yeah,
Meta's running hundreds of eBPF programs on every server. Netflix uses it, Google uses it. It's seen pretty wide adoption now, and the people pushing this technology have really thrown their weight behind it. Yeah, it is a little bit of a cop out to say like eBPF, implying that eBPF would have like a stable API over the last 5 years, because it hasn't. But I think it's the direction forward for when we look at how to do extensible operating systems in production right now.
Nice, cool. So you've used this and you've designed a DBMS proxy, which I guess is the star of the paper, Tigger, and I think it's a great name as well. I like the names of things, and I guess I can guess why it's called Tigger, right? But yeah, I'd like to know more about the actual naming discussion and who came up with that and whose idea it was. But yeah, tell us about the design and implementation of Tigger. Then there we go. The floor's yours.
Well, we can do a quick derail on the name. That was because of my wife. She's a big Winnie the Pooh fan, and I think I mean, we've seen these weird Winnie the Pooh movies. Like I read a couple years ago, like Winnie the Pooh went into the public domain. So that was why we see these weird, like Winnie the Pooh horror movies now. Like they're just making weird stuff with that license now. And I think when I first submitted the paper, I was just like, oh, Winnie the Pooh's in the public domain. I can use the name Tigger. They won't sue me. They being Disney, I guess. And I realized later that I guess Tigger was in a later book, like a year or two after. So Tigger, the character, wasn't actually in the public domain yet. So it's not actually clear to me where that stands right now. So we're just not going to tell Disney about any of it. But hopefully they're not watching the database research community.
You never know. Waiting for that email from the lawyer, right?
I hope not. I can't afford those legal bills. So I mean, when we designed the proxy, the basic idea here was, let's use this idea of user bypass, of avoiding going to user space, to sort of fast path the common operations that we see out of these database proxies. Like, let's just take PG Bouncer. It's like I said, it's actually a pretty simple code base to read. It's single threaded. It's written in C. I was pretty familiar with the Postgres code base, so C was comfortable to me, and so was the protocol. And take that, you sort of surgically insert some short little eBPF hooks and events that need to fire in order to get these eBPF programs to run. But the idea was like, okay, for these common operations like connection pooling, where effectively what the proxy is doing is it's reading a socket, it's applying Postgres protocol specific knowledge, seeing like what's the transaction status, what is the message that actually showed up? Is it a query? Are we changing the settings? What is it? Figure out which backend to send it to the correct backend. And then on the server connection, when a response comes back, it's figuring out who does that belong to, what is this message? It's usually a query result, send it back to the correct client. That's not that complicated to express in it's not a very complicated protocol. So, you write these eBPF programs that understand the Postgres protocol for these common operations like query and result redirection. And you put that in the kernel and you hook that into like the networking stack of the operating system. So for those sorts of messages, hopefully the common ones, query results, you never have to slip those to user space. You never have to wake up a user thread. They don't have to call a system call and do extra buffer copies and sort of all the trouble that goes along with running a user space application. You can just handle that in the network layer of the kernel when it runs on a software interrupt, when the message arrived, and send it back out to where it's supposed to go. And then for the less common messages like changing settings or something like that, you just slip that to user space and you let the user space component sort of handle that stuff. So Tigger is sort of a hybrid user bypass application where you take PG Bouncer and then you embed all this application logic in the kernel with eBPF specifically to handle things like connection pooling. And then we also implemented another feature, I think was workload mirroring, to be able to like replicate a workload between multiple backends. But so yeah, we started from PG Bouncer and that worked out really nicely for us.
Nice, yeah. A quick question on the hybrid aspect of it there. And is there any way? Again, I don't know whether this is actually a valid question, but say you implemented for all of the operations the opportunity to either use to go straight to through the OS or to use the user bypass path. Is there a way that you can sort of like, okay, after a certain threshold, switch to using user bypass because it's now more, you're going to get more like savings in some way than just send it to the OS, right? Or in an ideal world, would you just skip the OS altogether and everything would run through the user bypass? You just chose not to choose for some of the less common operations because there was just no point for the workload. Or is it some sort of like dynamism? That's the word. I can't think of the word I'm trying to say. But yeah, maybe half of my questions come across.
Yeah, I mean, so you could certainly figure out if there's like a sweet spot for how many, how much of the work to do in the letting it slip to user space. And in fact, like the resources are finite in the kernel in the sense that like you sort of have to say when you start the system, like how many sockets are we actually going to let like run these sort of user bypass programs? And at some point that will become saturated, and even queries and the responses could slip to user space if like we couldn't handle it in kernel space, because like the kernel adds these constraints about like you can't wait, you can't yield, like everything needs to like happen right now. So if the resource isn't available to do something when that event is firing, the only thing you can do is slip it to user space and sort of let it actually sit in a queue or a buffer and wait for it to actually be pulled off that buffer. So user space is sort of this fallback slow path when you can't actually service it in time. If every software interrupt handler in the kernel is already busy running one of these sort of user bypass programs to handle the connection pooling, you have no choice but to sort of slip it to user space. So in that sense, you sort of get dynamism for free. But we also, you sort of alluded to this. We sort of went after queries and the results because we're like, well, that's where we're going to get the most bang for your buck. Like there are certain other message types that the protocol will drop in, but we're less interested in those. And then there are some actual limitations where certain message types you just can't handle with user bypass in kernel space. You just couldn't do it. So certain forms of authentication messages, like if you're using something more complicated that requires hashing with a specific hashing algorithm for passwords or something like that, a lot of those algorithms you either can't express in a program that will satisfy that. There's this BPF verifier that sort of like the kernel has to make sure your program doesn't run for too long. So either the hashing algorithm would either isn't going to run in time to satisfy the verifier, or it's too complicated. And you can't link in external libraries to a BPF program. So I couldn't just grab an off-the-shelf hashing library or authentication library and run that in BPF. So we really just focused on queries and their results and slip everything else to user space. One, from an engineering standpoint, two, for bang for your buck on most of these workloads.
Yeah, nice. On the engineering effort there, how long did this sort of take you to implement, and how easy was it to sort of work with eBPF and the Postgres? You're familiar with Postgres anyway and PG Bouncer, so maybe that kind of eased the job a little bit. But yeah, how difficult was it?
So it wasn't too bad. It was probably only a couple months of engineering. It wasn't too bad. I don't know what that means to different people based on when you say a couple months of engineering, because some people are working 100-hour weeks, other people are working 35-hour weeks. It's hard to say what that means. The hardest part is when your BPF program fails, particularly with the verifier. It's very opaque why it failed. So the verifier is this when you load an eBPF program, and I'm going to go back and forth between eBPF and BPF just because they're the same thing, but one's easier to say than the other, I guess. But like what the verifier does when you load your program is it's trying to verify that your program is going to terminate. And it's not going to access memory in a bad way. It's not using APIs it shouldn't. And when it thinks you've done something wrong, it just yells at you in assembly, basically. It throws a bunch of BPF bytecode, which just looks like assembly, basically. And you have to try to figure out, like, oh no, what did I change and what went wrong and why is it angry at me? So that's where you lose most of your time with writing BPF programs. The logic itself, like I said, the Postgres protocol I was pretty familiar with already. There's okay blog posts and like YouTube videos where people discuss BPF, but the documentation is actually quite poor. And that's part of the moving target thing. Even the official like man pages and Linux kernel documentation is pretty rough. Your best hope is to actually look at samples in the Linux kernel code repo. Like the samples are pretty decent, and because they have to compile and still run every time they do a new kernel release, they should still work. So you spend a lot of time reading kernel samples to understand like how the APIs actually work, because the documentation is bad.
Right, cool. Yeah, so right. Awesome. Let's talk some numbers then. So you've dropped a few numbers in throughout the chat so far, but can you tell us more about your experiments, how you went evaluating Tigger, and what your setup was, what you compared it against, and some of the results?
Right. So for the evaluation that ended up in the paper, we ran, I think, everything in AWS EC2. For us, that like putting it in sort of a cloud native environment, I guess, helped strengthen the argument that this is really a problem it's a cloud scale issue, right? Like, and even in our case, when we're talking like 10,000 connections, some people would argue like that's not a cloud scale problem. But for us, we put it in EC2, so we could reason about data center latencies and tens of thousands of connections. We used at the time whatever their modern compute instances are, like the C6Is, I think. Everything was run in Ubuntu Linux, but really any modern Linux kernel should support like the BPF features that we needed. And we compared against, so I mean, I've discussed PG Bouncer. That's the standard option when you're talking about a Postgres proxy. We also compared against, I also alluded to Yandex's Odyssey. And again, like Odyssey is it's a complete rewrite of PG Bouncer. They kind of throw every trick in the book of like getting a fast user space application that they could reason about in terms of like how some people argue you should design modern parallel applications. So they rely on tricks like user space coroutines to get a lot of parallelism in user space, and it's the code it's impressive but tough to read. Like they wrote their own assembly to handle. They're not using like the C++, because I don't think that coroutine stuff went into C++ till C++ 20. So I think they wrote their own coroutine stuff that they have all the assembly instructions there to save the stack and swap that stuff in and out. It's a complicated piece of software, but they argued it was necessary to get the performance that they needed. And then today, I mean, I think we'll only talk about YCSB, which is the Yahoo Cloud Service Benchmark. It's effectively exercising a key value store over the Postgres wire protocol. This wasn't running on like localhost via stored procedures. So we actually use 3 servers in every experiment with an asterisk. The one experiment where we don't run 3 servers, we run 2 servers because we wanted to see how it compared to Unix domain sockets. So we wanted to actually put the proxy and the database system on the same box, which is what Yandex does. So people deploy these proxies in a lot of different ways in the real world. Some people are putting them on the same box and talking over Unix sockets with the database system. But there's a lot of design options there. But for us, we typically ran 3 boxes, one beefy box to be the workload generator running Benchbase to run things like YCSB and TPCC. The proxy was generally on a more constrained 2-core box because people typically aren't throwing a ton of resources at their database system proxies. And then we had Postgres running on a separate dedicated server, again, with a bunch of CPU cores and memory to hopefully make it such that Postgres wasn't often the bottleneck, because that was a bit of a challenge with sort of, if you want to benchmark proxies, you got to make sure your database system isn't the bottleneck, right? Like you want to try to actually look at the performance characteristics of these proxies. So that was a little bit of a challenge.
Yeah, nice. So what were the results then? Give us the highlights, the headlines.
Yeah, so I mean, one of the results that stood out to us was, so if we just run the YCSB benchmark at like max throughput and just say, okay, what can these proxies actually push? For like a 2-core box in EC2, PG Bouncer and Odyssey could do about 33,000 transactions per second, and Tigger could do 45,000. So over 40% increase in throughput. And the reason I highlight that one is this was a severely CPU constrained scenario. There's only 2 CPU cores. So we're sort of seeing the benefits of the CPU efficiency of Tigger there. And so one thing we did in that experiment is we actually scaled the size of the proxy box. We threw more compute resources. And in particular, this would benefit Odyssey more than anything, because Odyssey expresses parallelism. So we were just kind of curious, like, how much CPU do you have to throw at this problem for Odyssey to catch up? I mean, it turned out you needed 8 times the number of CPU cores at 8 times the cost to actually get equivalent performance as Tigger's sort of baseline. So it was this huge compute cost for Odyssey in order to be able to catch up to what Tigger was able to do, which with a much, much less expensive box. So we sort of wanted to try to understand that, like what's actually going on here. So one of the things we did is we sort of profiled all these applications, and it's difficult to sort of describe charts and figures in an audio setting. So I'll try to keep it sort of high level. So like, okay, let's run YCSB, and what we want to do is we fix the throughput. So fix the throughput at the proxy. Sort of nothing's really bottlenecked in this scenario. The workload application isn't bottlenecked. The proxy isn't bottlenecked, and the database isn't bottlenecked. Everyone's able to hold like this 2,000 transactions per second sort of throughput with like 10,000 clients on the front end. And then we did some CPU profiling and said, okay, where are these proxies actually spending their CPU cycles? And as expected, PG Bouncer and Odyssey had like the same amount of time spent in the kernel and in software interrupts, which is just sort of another way of classifying like doing network work in the kernel. They're handled by these sort of software interrupt handlers. And Odyssey actually used more time in user space than PG Bouncer did. It's sort of this complicated user space coroutine setup actually ended up using more CPU cycles in order to accomplish the same amount of work as PG Bouncer. Now, if you throw a bunch of compute at it in parallel, obviously it can pull ahead. Like that's worth the cost for some folks. But then when you compare against Tigger, there was no user space CPU time, unsurprisingly, for this sort of workload. All the work's done in kernel space. And there's actually even less time spent in the kernel and software interrupts, which is a little counterintuitive, but it's able to handle all of its work in a single software interrupt. It's able to handle it all on the receive end. Something arrives at Tigger, it immediately figures out what to do with it and sends it right back out. You don't actually have to handle another sort of software interrupt or more kernel code on the transmission side. So you're actually reducing the total number of CPU cycles even spent in the kernel to sort of apply something like user bypass.
Awesome. So it sounds like a win on all fronts then. So I mean, I always have to ask this question, and I got told off once for asking, are there any problems with who was it? I can't remember who it was. I'll have to edit this bit out. But I asked them, are there any what did I say? Scenarios in which your tool, whatever it was, doesn't perform well? And they said I should ask, is there any scenarios in which Tigger is suboptimal? The way I should ask these questions. So yeah.
Yeah. So I mean, I alluded to some of the problems with Tigger and maybe user bypass of just like eBPF is still not the friendliest environment. Like someone can't just say, I'm going to take my application, I'm going to apply user bypass the way Tigger did. Like, could someone use Tigger in production as like their proxy? Absolutely. Would it make sense for everyone? I don't know. There's a lot of reasons people are still, like I mentioned, sort of these big companies that are all in on eBPF. It's not clear to me if you need those sorts of resources in order to adopt eBPF, though. Like, could these small companies who are just deploying PG Bouncer to sort of scale out Postgres, like, would they feel comfortable deploying an eBPF backed application? I don't know. Like, do they have the compute resource or the engineering resources to vet these BPF programs and make the judgment call of like, should this be put into production for us? Because like these programs have to run as root, or you effectively need like sysadmin capabilities in order to load eBPF programs. So the engineering decision of whether you would actually want to take this approach, I'm not sure what that looks like in the real world in terms of like what companies are making the value call. Like obviously the big companies are making the value call saying we're in on eBPF. It's worth the engineering complexity to get these performance wins that I kind of describe here of like, you can solve the same problem using far fewer CPU cycles if you can get the BPF program written and are comfortable putting it into production. The other thing is like you're trading off like complexity of understanding your user space application for understanding the Linux kernel. Now, to be fair, to get really good performance out of something like Odyssey or any other network application or even database system, you do have to tune things like IRQ affinities in the Linux kernel and like understanding how like sort of, soft IRQs are handled and how it handles sort of top half and bottom half of interrupts and deferred aspects of interrupt. Like there's all this complicated inner workings of how things like interrupts are handled in the Linux kernel. And if you really want to build a fast application like Tigger to apply user bypass for network IOs or even storage IOs, you're going to end up reading a lot of kernel code to understand like how to, one, where to sort of surgically insert your solution into the OS stack and how to get the best performance out of it. Because if you don't tune the kernel right, you're still going to get quite poor performance out of this, I think.
Cool. I guess, yeah. So where you said that you could probably use Tigger now in production if you wanted to. So where do you go next with Tigger, and what's next on the research agenda? Is it productization of it, or are there other features you want to work with? I know obviously you're coming to the end of your PhD, so you've probably got other sort of pressing matters, but where would you go next with it?
I think there's kind of two directions you could go off of sort of this paper. One is just sort of, I think we alluded to this in sort of future work, is like, and I alluded to this earlier in our conversation of, there's a lot of features that proxies can support. Things like sharding, things like query rewriting, query result caching. Does it make sense to push some of those sorts of things, more features? How far can you go with eBPF to satisfy the verifier and storing things in the kernel? You can sort of think as proxies as sort of, if they're this sort of middle box sitting between clients and the database system front end. We started thinking as well about like, well, in these distributed cloud data warehouse systems, you have these shuffle nodes that are sort of ephemerally holding onto data as well, right? Like they start crunching on some results, and they do one query operator, and then they forward it to a shuffle node, which sort of redistributes it to another set of workers. It's sort of the old MapReduce thing we've had around for ages now, it seems like. And these shuffle nodes are sort of ephemerally holding onto data as well. Like, does that make sense to be a sort of application class that you push into the kernel? You don't have to go to user space for things like shuffle nodes. The problem is, like, in the same way that what is a proxy isn't standardized, what is a shuffle node isn't standardized either. So like, I think BigQuery has dedicated shuffle nodes. Redshift, it's just another operator to them. So like special casing shuffle node logic may or may not make sense depending on the cloud system you're talking about. And the other thing that I think would be interesting that came out of this work, it would, I think, benefit the academic community to sort of just have a survey paper that looks at like, how do you deploy these database system proxies and what are the trade-offs? You know, we tried to do the best we could with the limited background section, the space that we had to sort of introduce this concept of database proxies to the community. But it raised a lot of questions of just people like, well, I have this workload. Would a proxy help me here? I have this many front-end connections and I have this many back-end servers, and would a proxy help, you know, my performance here? And it's like, I don't know, you kind of just got to try it. But it would be interesting to see like a sensitivity analysis in a lot of different dimensions to understand like how much compute should you throw at your proxy? How many persistent connections should it have for a given workload? And you start getting into like, you could get into queuing theory stuff of just like, okay, well, you could probably prescriptively say exactly how many persistent backend connections your proxy should have given X number of front end clients submitting work at X rate. Yeah, you could solve that problem, apply some queuing theory, but like something prescriptive to say like, these things exist and they have all these interesting properties and capabilities, but there's all these different trade-offs. Like an experiments and analysis paper would be really interesting to see there.
Yeah, for sure. We need that sort of canonical paper, right, that we can reference. And rather than, I mean, obviously you kind of say, oh yeah, just go and suck it and see and find out whatever works for you. But yeah, we would definitely benefit. I think the community would benefit from having that sort of work done. Because, I mean, you obviously you've done a lot of extensive background research. How much work has there been in the database community from the research side on this sort of area? It feels to me sort of very untouched still. I mean, this feels like an initial sort of foray into it, but it feels very much sort of like a nice wide open area of research, possibly.
Yeah, I mean, effectively none. So if we can, I think you were going to ask a question, I think, coming up that's just sort of like, what's the most interesting lesson I learned while working on Tigger? I'll get into that now. So like there's been very little academic discussion, particularly on database proxies. The network community talks about proxies and you go look at NSDI, people are doing proxies for different things, oftentimes application layer proxies, but sometimes not. Sometimes people are just talking about like, how do you do faster TCP proxying? But you alluded to like, there's not a lot of discussion in the community, and that's a bit of a double-edged sword from a researcher standpoint. Like we were really drawn to this problem because we were like, it seems like everybody's deploying proxies in production when they need to scale out, particularly MySQL or Postgres. But like, database systems you start with as you're doing your startup and your business grows, and the first thing people grab is a proxy to help scale out their backends. But no one's talking about it in the academic community, like completely oblivious to it. So on the one hand, as a researcher, you're like, this is super attractive. I can't wait to work in this area that like no one else is thinking about. The downside to that is no one knows what you're talking about. Like the reviewers have no context, and it's on you to write that context and make them care about the problem and get them to understand like this is a real problem in industry. People are using these things, they're solving a problem, and it can be good to sort of plant a flag on a problem, but it's your challenge to make the community care about it. So like I alluded to, like I think we would be served by this sort of survey paper, this sort of, I wish I had written that first, because then you could have cited it. Like here we had to do everything in the background section, and making the community care about it was really challenging with the limited sort of page count that you usually have in a background section of a paper. So like it's a very double-edged sword to sort of see this verdant, empty pasture of research and go running towards it and realize that the responsibility is on you to make the community care, and get them to actually understand that it's sort of a real problem.
Yeah, that's definitely a fun challenge, I guess. But I do feel that there often is that kind of disconnect between what's happening in the real world and what's happening in research, right? It's really hard to sort of bridge that gap and then get people in either space to care about the thing the other person cares about, right? But yeah, no, I definitely agree with you there. Kind of going on from that a little bit is, can you tell us more about the backstory of this paper? And so how did you come across this being a problem? You said, like, I observed it, like loads of people were doing it and no one was kind of in the research world was thinking about it. How did you kind of get to that point?
So it was sort of a bunch of different interests coming together. So I had already been exposed to BPF for some previous work I had done where we really relied on BPF for observability. So I had sort of dipped my toes into that community, learning about BPF. Another was sort of just reading what people were saying about scaling out their database systems, where they're talking about like, hey, here's how I had to deploy PG Bouncer to solve this problem, and what are the trade-offs of PG Bouncer MySQL. Some of it was sort of like, off the record conversations of just, Andy is working, he's got his startup on the side, and he's just like, man, a lot of people are using proxies these days. Just sort of this anecdotal observation that seeing these things a lot in production, and an aspect of database systems that we hadn't really reasoned about as an academic community. And increasingly just thinking like, these are interesting applications. There are interesting problems you could solve by putting a box in the middle, and because suddenly you have observability of the entire workload. You can permute the workload if you want. Like there's all these tricks you can do if you have this sort of middle box. So that got us really excited about this idea of like proxies are sort of accepted by the industry community as like a way to solve database system problems. And then my background in just sort of performance engineering of trying to figure out like, why is code slow? How could you make it faster? And it's like, oh, wait, this code is slow just because we're interacting with the operating system and because we're going to user space to do the work. Do proxies sit in this perfect, like, the Venn diagram of like the application logic isn't that complicated. It sits in the network layer. So, we could use BPF to sort of try to solve this problem. And there's enough, people in industry, they're not papers we can cite, but people have written enough online that they can at least say like they're used. And that there's a little bit of credibility there of just like, this is an actual real problem space.
Yeah, nice. When you're kind of working on Tigger, then I'm not sure if we've covered this so far or not, but were there sort of any? Because I like to ask this because obviously research is non-linear, right? There's ups and downs. You hit dead ends. Were there some things that you tried along the way that you kind of that failed, and some of the more war stories kind of with Tigger?
Yeah, I mean, I think part of the experiment process and part of the design process was trying to figure out like, for these BPF programs, there's a lot of different layers you can hook in the Linux networking stack. Like how far down do you want to push your application logic? At an extreme end, you can push it all the way down to, if your NIC supports it, down to the hardware. So that you could basically be intercepting network communications. They're called XDP BPF programs. And depending on what your OS and what your NIC supports, you can push your logic really far down. So we started actually looking all the way down there. Like, it's like, could you handle this at the XDP layer? But you lose some of the abstractions that we rely on of just like, okay, well, suddenly you're below TCP. So we looked at trying to figure out like, could you make this work without doing TCP? No, you really got to maintain your own TCP state machine. Like there have been other efforts to use BPF to sort of fast path network communications, and people just say, we use UDP because it's a much easier protocol to reason about and sort of maintain our own state for. But like we spent a little bit of time trying to figure out like, could we do our own TCP state machine down there? Would you get the performance benefits? Like, no, move up a layer, let the OS handle TCP for you. It also gets you access to things like you could use kernel TLS. So you could still use SSL. Like people could still use encryption to talk to the database system. Like if you push all the way down to the XDP layer, you sort of lose those capabilities. So we spend a lot of time trying to figure out like, and some false starts of like writing code at the XDP layer, different layers in the Linux kernel. And this is where I said like one of the challenges of BPF is like you spend a lot of time understanding like the internals of the Linux kernel and the software stack itself, of like just being proficient, figuring out how to write an application that gets you the performance you want. You actually have to understand a lot of the Linux kernel, which is kind of a pain. So yeah, like some was sort of experimental, like trying to make it work at XDP. Others was just spending a lot of time understanding the ins and outs of the kernel stack, and arguably losing time on that. But like that's part of the process, I guess.
Yeah, for sure. And you never know at what point in the future that knowledge you've gained by going down that path is going to help you out with something else, right? So it's always
it's not lost
always
time.
Positive. Exactly. Yeah, you've learned something, right, which is always good. And cool. Yeah. So I mean, obviously, Tigger's very sort of pioneering in the sense that of the technology it's using to solve this problem. But what kind of impact do you think Tigger can have maybe on like someone's day-to-day life as a software engineer or a data engineer, and what sort of wider sort of ramifications do you think this work can kind of have for the database community as well?
Yeah, so I like to think that Tigger is just more of almost a case study or example for like the loftier goal of this idea of user bypass. So that's actually sort of like what my dissertation will actually end up being on, this notion of like, we want to design software that sort of contrasts this kernel bypass approach and instead push application logic into the kernel. We can do this now because of things like eBPF. We don't have to load kernel modules. We don't have to compile our own kernel. So for like the average person, like a lot of people don't need a database proxy, but are people doing applications or writing applications or relying on applications where like, particularly network or really stuff related to IOs, where you're bringing data all the way to user space, doing very little with it and either discarding it or sending it back out. those may be opportunities for something like user bypass to have an impact. You don't have to go to all the way to user space. And sort of like at a high level, there's this quote from Mike Stonebreaker from over 40 years ago, where he's like, the bottom line is that operating system services in many existing systems are too slow or inappropriate. And that sort of created this mindset in the database community that like the OS is not our friend. It's very adversarial between database system designers and operating system designers. And I feel like I've always taken issue with that in my time as a graduate student. And like, I will argue with Andy that like, we can coexist and we can have this symbiotic relationship because of things like particularly eBPF. Because before that, the syscall interface was a little too rigid. You couldn't quite get the kernel to do what you wanted it to do, but now we can actually sort of tweak the kernel just enough to get what we want from it as database system designers or general application designers, network applications, whatever it is. I'm not going to argue with a Turing Award winner, with Mike. But like the landscape is changing enough now in the OS community that application developers, high performance application developers, if they want to push their logic down into the kernel, apply user bypass. I'll keep saying that phrase because I want to coin that. But that I think Tigger's more the case study for something like that working and showing the benefits of it. And absolutely there are trade-offs, but I think in the right places it can be pretty impactful.
Yeah, well, I think the flag has definitely been planted. So yeah, hopefully it can be have a lot of impact going forward. Cool. And I know you've worked on lots of other cool things across your PhD. So maybe you can kind of just give the listener a rundown of some of the other things you've worked on over your time as a grad student.
Yeah. So I mean, when I first started doing research at CMU, we were very heavily invested, and we still have students working on these problems of sort of these self-driving or autonomous database systems, sort of machine learning for systems. So when I sort of alluded briefly earlier that I'd done BPF for observability, that was actually to collect training data for some of the autonomous database system, self-driving database system research we were doing. So I've spent a lot of time working on, thinking about these ML for systems problems. How do you efficiently collect training data for these sorts of systems? Working in that actually required me to help build an entire system from scratch. We have a in-memory database system called NoisePage that sort of took a lot of inspiration from Hyper with how we do MVCC and concurrency control and logging and stuff like that. And then, so going forward, we continue to do sort of this self-driving database system research, looking at things like, again, training data collection has this huge overhead. Looking at things like how do you create a standardized API for this problem, something like a gem from the OpenAI community, as it relates to the problems we have in database systems, and sort of trying to bring ML to solve some of the problems there. And then personally, sort of going forward, looking at, again, how do we do user bypass in more contexts, and maybe the crazy question of like, well, what would an embedded database system for eBPF programs look like? What sort of rich applications would that open up? So those are the sort of the problems we're thinking about now. If you can imagine something like a RocksDB or a Berkeley DB, if eBPF had access to something like that, what sort of problems could you solve?
Yeah, nice, cool, awesome. So yeah, I my regular listeners will know that this next question is my favorite question, and it's all about the creative process. So I'd like to know more about how you approach idea generation, Matt, and how you then go about selecting the projects from the ideas you've generated. Yeah. So your creative process, what is it? What's the secret?
So I'm lucky enough. I mean, a lot of this comes down to, and it's sort of a cop-out answer in graduate school, right? Like it comes down to your relationship with your advisor, right? Like, so for me, I have a lot of freedom to sort of think about the problems that are interesting to me. Sort of, a lot of it is obviously reading, but it's not just papers. Like I said, a lot of it was reading what people are saying about database systems in industry, keeping in touch with sort of wanting to keep grounded with what I think are real problems that people are trying to solve with database systems, and what are they facing in on the industry side, and balancing sort of the research problems with the industry problems. And thankfully, I'm surrounded by just a lot of smart people in the community whether that's at CMU, whether that's in the broader database systems research community, or even broader just computer science research community. Like there's so many people that we can just sort of bounce ideas off of. So I get to sort of like write toy implementations and think about a problem for like a month or two and try to prototype a solution for it. And like, it's very data driven and trying to figure out like, what are the workloads that make sense? And does this actually solve a problem there? And what are the trade-offs? And then the paper just sort of grows from there. Usually the research project of like, okay, this looks promising. And then you end up usually rewriting the whole thing and actually going all in, and, you know, you throw away your toy implementation and start actually, okay, let's do this right now. So it's very iterative. It's a lot of toy and code, experimental code, early prototyping, always making sure that like everything's backed up by numbers early on, and not just going with your hunch. Like again, sort of looking at it from a performance engineering standpoint. Like make sure you can measure the problem, because like if you can't, you're gonna have a hard time justifying its existence. And that's true in the research community. That's true on the industry side. Like if you can't measure the problem, you're going to have a hard time justifying that it's a problem at all, and that your solution is, you know, deserves merit.
Yeah, I know that's a really nice answer to that question. It's another one for my collection. Yeah, thank you. Great stuff. Yeah, so now you've got another opportunity to coin new phrase. So what's the one takeaway you want the listener to get from this podcast today?
I'll say that the operating system is not your enemy. As much as Andy will side eye me every time I say that, you know, because he says these operating system services are they're not written for you. And there are comments from, you know, Linus Torvalds saying denigrating things about database system developers as well when we ask for things in the kernel. Like it's a contentious relationship, but I do think there's a, you know, we as high performance application writers and them as the operating system community, like we can coexist, and we're getting the tools and the common language to sort of solve problems together without having such a blunt instrument of, well, I'm going to go full kernel bypass and take everything away from the operating system and do it all myself in user space, or go the opposite direction and write like a unikernel that isn't really able to be put into production either. There is a happy middle ground that actually solves a lot of problems, I think.
Yeah, awesome. That's funny when you've been talking about this. I can't get the image of, you know, in Anchorman where like the rival news groups kind of come together and have like a mad fight. That's the image that's been playing in my head over and over again. But anyway, yeah, cool.
That I think we could do fun. That could be a fun prompt for Midjourney. I think we could find some way to do something fun with that, actually.
Yeah, cool, great stuff. Well, let's end it there. Thanks so much, Matt, for coming on the show. It's been a fantastic chat. If the listeners interested in knowing more about Matt's work, we'll put links or everything in the show notes, so you can go and check that out. And Matt, what are your socials? Where can we find you on X, Twitter, whatever it's called these days?
I think I still have an X/Twitter account. I don't use it. I just got Blue Sky. I'm not a social media person. I'm on LinkedIn. People can find me if they want to talk about my work there. Shoot me an email. I'm happy to chat anytime. It doesn't have to be about my work. It can be about grad school. It can be about anything. I'm always happy to hear from folks.
Awesome stuff. Great stuff. And yeah, I guess with that, we'll see you all next time for some more awesome computer science research.